Okay, so yeah, so it's a kind of a bit of a background on the stuff that I do. So I'm a postdoc here, but not here on the the other side of the West Cambridge in the computer science department. And kind of the general things that I do in life is to look at the theory of dependent types, so the sort of formalism that underlie most of the proof assistants out there, maybe with the big exception of Isabel, but like Lean, Coq, F-star, Agda, Idris, all kind of rely on more or less a similar formal system. And I try to not only work on this meta theory, but ideally formalize some of these things in proof assistance. And kind of the main things that I've been doing in the past are working on this kind of big MetaCoq project, just about trying to formally verify as much as possible of the theory around Coq inside of Coq itself. And then a kind of a second, more research project about kind of in the same space of formalized meta theory, but on kind of a different angle, working on logical relations. And I'll tell you a bit more about what this is in a moment. But I figured that I could have gone in kind of gory details about these things, but I felt that probably you maybe are not too familiar with this sort of landscape. And so that I would rather give you some sort of broader overview of kind of the sort of ideas that are out there, what do these systems kind of look like, and what sort of properties we care about in them, so the sort of things that we want to prove in these sort of projects and so on. And since I actually don't know how much you know, I want to have some quick show of hands on kind of where you're at. So are there people in the room that have never used a dependently typed proof assistant, never touched one? Kind of, okay, a little bit, okay. Are there, who is a kind of a regular user of Lean or Coq or Agda or something? Okay, kind of, okay. Who has some idea what a dependent function type is? Okay, excellent. And who has an idea what canonicity means? Okay, excellent. So that's I was actually quite not too bad about my predictions. So I hope this will kind of hit in the right place. Don't hesitate to ask me questions while I go. I mean, the point is to kind of give you an overview of the thing. So please interrupt me as kind of more details or things like that as I go. And I'm a computer scientist, so of course I want to start with a demo of something to kind of motivate a little bit the sort of things that I do. And because I know that I think most of the crowd here are Lean users, I installed Lean especially for you, because usually I'm a Coq user. And so kind of to show the sort of something that I've been actually working on quite recently. I'll come back to this at the end of the talk, but kind of to give you a little bit of an overview. This is working with coercions. So I don't know if you know about this, but probably you do. But in Lean, there's this ability that if you have kind of your types don't really mismatch, you have for instance, something that looks like this. So this is a presentation of strictly positive natural numbers. So you can define them as a inductive type, and then you want to define a mapping from them into the regular natural numbers, kind of just doing the obvious thing. But then you want kind of the type checker to be aware of this function and to kind of insert it in the right ways to kind of make things fit, so that you don't have to every time by yourself say, oh, by the way, this was a positive thing, but I wanted a natural number, so please insert this function. And so this is what this COI business is doing. This COI stands for coercions, and you're kind of declaring things that oh, I have this coercion function from positive to nat, and then you're telling the type checker to insert it in the right places. And then there's also one, which is, I think, in the standard library of Lean, that also you can have a coercion from natural number to integers, which is kind of the thing that you'd expect from mathematics. And then because I'm a computer scientist, I want to do something a little bit more funky, which is basically I want to extend this story to lists. So whenever you have a coercion from a type X to a type Y, I also want to construct a coercion between the list of X to list of Y, which is just going to apply. So this map function which just applies the function on all elements of the list. And if I think it's a kind of a very natural thing to want. If you're a category theorist, and this is kind of the action of the functor, and you'd really want the type checker to be smart enough to insert that by itself. The problem is that if you do that kind of naively in Lean, you end up with weird problems. So if you start with a list of positive numbers, and you're trying to equate this list to itself, but kind of telling it explicitly that you want to go through natural numbers first, and then to integers. And these two, like the left and the right side, really look like this. They're the same thing. Like you added a little bit more of annotations, but really they're the same thing. And if you try to do kind of the reflexivity proof there, Lean complains that it's not working. And you can try to look at the error. And actually what's happening there is that there's kind of two ways you can go from this one to this one. One way is to map with the composition of the two coercions. And the other one is to do two coercions, which are both mapping of the individual coercion function. And the kernel of Lean at least doesn't know about the fact that this is fine. In other words, that map is has the functor law, the composition law of functors. And it's sadly complaining here. Now, if you see these sort of things, and actually, like, this is just one example of coercions going wrong. So kind of to sum up, in some sense, we want these coercions to be transparent. Like there's kind of two ways to coerce this L to the type we want it to be. And in some sense, we want to think that all of these ways to do the coercion should be the same. So like we don't want to think about these coercions. And the problem is that in the current implementation, this is not really what's happening, which is why this reflectivity failed. And actually, this is kind of maybe a slightly artificial example because like kind of set up the types just to make the thing fail. But trust me, this happens in kind of more complicated settings. And actually, if you go look at the GitHub repository for kind of all of the big like dependent type proof assistants, you get issues that say that coercion are not working well. This one is an F star, this one is an Agda, this one is in Coq, and this one is in Lean. And I mean, some of them are close, but I think the close one are actually mostly saying like, oh, this is a hard theory problem. So we don't want to like kind of solve it in this issue. So we're just closing the issue because it's too hard. And so, or like, I mean, this is not a problem that you want to solve easily in just one GitHub issue. And so if you're faced with this sort of things, there are kind of two ways you can go about it. You can try to say, okay, like I have a lot of fancy machinery in my proof assistant. There's like all sorts of tactics and type classes and all that. So maybe I can kind of use all of this sort of machinery to kind of patch the problems on the kind of her higher layer. And that's one of a very fine solution. Usually it's kind of the easy solution to go for. But then my usual solution to this is that, no, this is not what I want to do. I want to kind of understand the type theory better, try to kind of recast the problem in some sort of theoretical setting to understand better what's happening. And then hopefully once we've done this kind of deeper understanding of things, we can come up with a maybe more principled solution that we can kind of import back in our proof assistant at the end of the day. So I won't tell you too much about coercions right now. I'll come back to it at the very end once we have kind of a bit more of context happening. But that's kind of a general, my general motivation for understanding type theory is this sort of things, like trying to kind of get to the bottom of all sorts of issues that can happen when you use your proof assistant, and hopefully by understanding things well, kind of to come up with a good principled solution to all sorts of these things and kind of make the life of users nice. Okay, and so now now I can try to start to get into the business of dependent type theory. And so first I need to tell you about the sort of objects that we're going to manipulate there. And so kind of the three main kinds of objects that we're going to manipulate are, is this on? Yes, it's kind of small, but okay, so we have these types, which are also used to represent propositions. That's kind of the big reason we want to use dependent type system is that there's kind of a nice relation between kind of the logical side of things, typically propositions, and the kind of more PL side of things where we want to think about types and programs and so on. And the idea is that this is kind of a nice and uniform setting to talk about these things all together, which is quite useful because you typically only need to implement things once and then you get them both for propositions and for types, which is very powerful. And then these types will be kind of inhabited by these objects, which again are going to be either proofs or terms, depending on which side of the fence you live in. And then the kind of third thing that we're going to manipulate in this kind of very basic theoretical setting are contexts, which on the logical side are basically a way of recording all the hypotheses that you have at hand. And so typically contexts are basically lists of types or like typed variables. So it's kind of a name saying like what type that variable should be living. And then we want to look at these objects and say that they have some sort of nice properties. And so kind of the next layer are these kind of typing judgments, okay? So kind of the main one, that's probably most familiar to you if you actually use the system, is this one saying that in the context gamma, a certain term has a certain type, okay? And if you're in logic, this means that assuming the hypothesis in gamma, T is a proof of that proposition. And I'll come back to a bit more of the relation of this with logic in a minute. But then we also want to kind of be able to talk about these things in a nice way. We need a bit more of stuff. We also want to be able that a type itself is well formed. Okay. So this is just saying that like the proposition A or the type A is a valid, well formed thing. And then we also want to compare these objects, because typically these, especially if you're on the kind of the computer science side of things, and you see these terms as some sort of program, you really want to kind of evaluate them or these sort of things. If you're kind of more on the logic side, you want them to have some sort of equational theory. And so this is what this relation is doing. This is called either conversion or definitional equality. I'll try to stick to conversion, but I might say definitionally equal instead, and they're really just the same thing. So what this means is that these kind of two objects, which are both at the type A, are somehow
a message from someone telling me to share your screen.
Ah, I am not sharing my screen. Why am I not? It used to work before. Let's see. I lost my share screen. Okay, let's do it again. Now I can do.
13 messages.
Oh shit! There you go. Sorry, I was not looking at Zoom.
Yeah.
So if I do this and I do this, then it's there. Okay. Okay, sorry for that. Okay. I think it is, yes. Okay, so for those that were not on the that didn't see the slides, so this is the judgment for typing, this one here. This is the well-formedness of types. And these two things here are saying respectively that these two terms somehow are equal or convertible or like something like that. And here, this is the same thing for types. And you can also do the same thing for context, that they kind of just always pointwise things. So I'm not going to talk too much about context because it's just kind of the pointwise thing that types do. And the thing to note is that this is somehow some sort of external judgment, in the sense that this is not something that you're going to give a witness for as a user. This is not something that you're going to prove. This is not the like kind of the, if you write an equality in Lean, for instance, this is not the same thing. This is some sort of external thing that your computer is going to check behind the scene. But the point is that, I'll come back to this in a moment, but you want this to be some sort of decidable thing, okay? Not something that requires witness and complicated arguments for. And then the way type theorists talk about these judgments is that we use what's called inference rules. And I'll try not to show too much of them, but this is the way we kind of talk to each other. So what this is saying, for instance, this one is that, okay, so maybe I'll start with this one because it has actual premises. So the idea of this rules is to say that if you want to show or to deduce this judgment here, saying that T has type B, it is enough, or you can deduce that from the fact that T has a type A, which is different from B, but then that the two are convertible or definitionally equal, okay? So this is kind of, you can read it kind of from the bottom up. If I want to do this, I have to do only the things above, or kind of the other way around. Like if I know these two things, I can also deduce this new thing. And so kind of the typical rules that we have kind of at this level of kind of just very abstract things, we have a rule for variables. If you have one variable in our context, and this variable is also a term, which has the type which was recorded in the context. This is kind of using a hypothesis. Our conversion relation is going to be reflexive and transitive, and also symmetric. I didn't include it here just kind of for brevity. And then this kind of the one big important rule, and the reason why we introduced this judgment in the first place is that basically from the point of view of the type system, two definitionally equal to convertible types are the same. Okay. And so this is kind of so the name logical framework hints at this at the idea that this is some sort of kind of general setting. And then in this general setting, we're going to be looking at various different type theories by introducing new types and new terms and new definitional equalities between them. Yes.
What are the sorts of types that maybe users don't work, but user would want to define as definitionally coercible?
So I'll give an example of this in just a second with a particular example. Okay. So this is these dependent functions. Okay. So in this would be written like this for the type. Okay. So this is kind of a function, but then the interesting thing about dependent types is that the image of the function, this codomain B, can mention the variable in some way. Okay. So this is not kind of your usual function. But then the way to build such a function is, well, kind of this is lambda abstraction, or like the usual kind of mathematical notation would be with a like an arrow, like x maps to t, which is any term that can mention x, and then use these functions by just a function application, which I write the type theoretic way, and not the mathematical way with parameters around the u. But I guess probably most of you are familiar with that. And then the type theory way of saying this is that we have kind of 3 rules to kind of form each of these things. So this is the rule for the dependent function type. Okay, so this is saying that if for such a dependent function type to be well formed, so this is really the type theoretic notation for this lean thing. You need 2 things. You need the type A to be well formed itself, and you need the type B to be well formed. And note that now we've extended the context with the extra x, which is kind of mirroring the fact that B can use that variable in some way. And then so the function one is kind of similar. So this function thing is going to have the dependent function type if again the type is well formed. And then in this extended context, the body of the function has the dependent type here. Okay. And the last one is the rule for application. So for the application to be well formed, first the function has to have a function type. And also the argument of the function must have the type of the domain of the function. Okay, so that's kind of the usual thing for mathematics. You want to apply function to argument of the right shape. The only, again, kind of new thing here is that this substitution operation, because B could mention the variable x, and we need to do something with it because x is not available here anymore. So what we're doing is we're going to replace x with the actual argument of the function. Okay, and this is kind of, this looks like kind of formalism in some sense here, but this is kind of actually a lot of the machinery that you need to kind of encode all sorts of fancy quantifier and all sorts of things like that. But actually the picture here is not complete because we need to also extend or like say how this whole machinery works with a definitional equality, with a conversion relation. And there's kind of 2 rules here. The first one is for kind of for people that have some sort of computer science background. This is kind of lambda calculus. It's called the beta rule. What it says is that if you have a function and you apply it to an argument, this thing is equal to the body of the function where you've replaced the variable that was used in the function by the actual argument. Okay, so this is kind of the thing that you do all of the time without realizing whenever you're manipulating functions in mathematics that were defined with this kind of explicit way. When you apply that into an argument, you do some sort of substitution like this. But here, this is now kind of codified in this definitional equality thing. And the second thing that we want to have for functions is this eta rule, which is a bit more mysterious. What it says is that basically, if you have something that kind of binds a variable and then immediately applies some function to that variable, okay, and that function doesn't mention the variable at all, this is just the exact same thing as the function itself. Okay, so this is kind of saying that, I mean, there's many ways to think about this, but the point is that we can't really like any function can be put in this kind of explicit form if you want, and that's quite useful in a bunch of settings. And so that's kind of the sort of rules that we want to put in there, are these kind of typically kind of computer sciencey things that like have some sort of computational behavior typically. And the reason why we only want to put these rules is that these are the rules that we kind of know how to play with the computer and kind of decide in a reasonable way. And I'll get back to that a bit more in a moment. Okay, and then I won't tell it too much here, but also you want all sorts of congruences for this relation. So like for each of these rules, you also have kind of a relational variant that says like, oh, if I have A, which is related to A prime, and B, which is related to B prime, then pi AB is related to pi A prime B prime. And then, so this is kind of the very basic setup, and there's a lot of things that you want that you can add in this logical framework. One thing are like kind of the basic thing that computer scientists really like are these inductive types or co-inductive types, which are some sort of initial algebras for nice functors, or which lets you define a lot of nice structures. So all things like natural numbers and lists and so on, but also all sorts of kind of predicates defined by induction, or all sorts of wacky things. This is a very, very good, powerful source of all sorts of definitions. And we really want those in our time theory. Another thing that's maybe more useful on the mathematics side, or the computer scientists use it quite a lot as well, are records. So basically ways of bundling all sorts of data together. So if you've ever seen kind of the textbook definition of a group, which is a set with an operation and an element and a bunch of equations as well, well, records are a way to kind of put all of these things together in one big bundle. And it's very, very useful, of course, on the whole kind of algebra side of things. And the last thing that we typically want to add are these universes, which are a bit more mysterious. They're basically types for types. So the typical rule that you have for these universes are things. So this type here is a universe. So it's a type, okay? But then the rule says that if you have an element of this type, then that element is a type itself. And then depending on the exact setup, you might want to have a separation between the types seen, the type seen as a term of the type, or the type seen as a type itself. And sometimes the difference between the two is blurred. And typically in implementation, you don't see this difference. And so you can just give a type as an argument to a function. But like the reason why you can do these sort of things, that kind of manipulating types with functions, is thanks to these universes. Yes?
It looks like it would laugh at type and type.
No, so that's the thing, is that this is also one of the reasons we want to put this separate judgment saying that something is a type, is that typically not everything, so not all the types that are well-formed types live in a universe, okay? So this is a one-way thing, right? If you have something which is of type, then it is a type, but typically not all things that are types would live in a universe, if that makes sense.
Okay. Yeah.
And so typically, like in the maybe to be a bit more concrete, if you're kind of used to lean, typically all the like type I, or like these, you have this kind of infinite hierarchy. So all of them would be types in the sense of that judgment, but you don't have one type where all of these live. So like you can't put one thing to the right of the column so that all of the type I live to the left, if that makes sense.
I think so, yeah.
So like I can maybe write it here. So there's not a U, so you have these type I. So they're all types in the sense of this judgment, but you don't have something such that type I is, let's call it U for universe. You don't have a single U so that all the type I's are of type U. Okay, and this is why this distinction is important. Okay, so like all of these are well-formed types, but they don't all live in the same universe.
Yeah,
Okay,
yeah.
and that's the point of these universes, that typically, so like the rule that you have typically is that you have like type I is of type J if like I is strictly smaller than J. You have these sort of rules, okay?
Yeah.
And so all of these type I are all universes, but the exact type that they contain are not the same.
Nice.
If that makes sense. But indeed, that's one big reason here, because otherwise, if we could do this kind of type in type business, then probably we would not need all of this machinery. No. But note that, for instance, another use of this is, again, we want often to kind of separate propositions from the general types. And this is also like propositions are going to be yet another universe that's different from the type universe and which will have some special rule of its own. Okay, and so all of this is captured in this frame. And then you might add a lot of other crazy things, but kind of these three ingredients already give you quite a lot of mileage. And then each time you introduce one of these things, you actually kind of replay the same recipe that I did with functions. So you need to define a new type, which was, for instance, the pi type here. Then what's called introductions, so way to construct things that live in that type. So here, this was this function, this lambda abstraction. You need to typically add elimination, which is how to use things of that type. So in the case of function, this was application. And then you want to add a bunch of definitional equalities, conversion rules. So typically some sort of computation rule that took like some sort of the beta one that we had, which is like how things compute. And then sometimes you also want to add some sort of uniqueness principle that look a bit like this eta thing, which is like yet another way to look at eta is like all functions are lambda abstractions. And sometimes you want to do that, but not always, because it's an easy way to break this adaptability. So that's one place where you have to be a bit careful. But kind of the general recipe always looks like this. Okay. And so maybe to kind of, as a way to understand this, because like I've been kind of showing things on the kind of all sorts of rules and so on, kind of the old school way, the very old school way of thinking about kind of logic, if you look at textbooks from the 40s or something, they're going to tell you about strings and about parentheses and about kind of linear things on the page and so on. And that's really terrible because you end up worrying a lot about details that have nothing to do with the point here. A kind of maybe a bit more abstract way is to think of this as some sort of logic, but recording witnesses, okay? So kind of if you always erase the terms of all of the things that I wrote, it kind of looks really like some sort of first order logic. I mean, the rule for the dependent function that really looked like the rule for universal quantification in first order logic, except that here we want to really think of the proof witnesses as objects that we want to manipulate and think about. And so we really want to record these witnesses. If you're more on the kind of the computer science side of things, you don't want to think of strings, but you rather want to think of these as some sort of syntax tree, okay? So kind of trees with nodes labeled by these operations, and then like subtrees, which correspond to the subterms in some sense. And then all these rules are kind of defining inductive predicates. So like the least relation that is symmetric, reflexive, transitive, congruent, and contains beta and eta and so on. And that's kind of a nice way to think if you're kind of living at the level of a type checker, because like typically your typical type checker will live with these things. I mean, not maybe the inductive predicates, but it will manipulate these syntax trees. Okay. You can actually go further in the abstraction layer. You can view this as some sort of grand generalization of like universal algebra, what's called this generalized algebraic theory. So the idea is this: if you start with universal algebra, it's very easy to turn to multi-sorted universal algebra. So think, for instance, if you want to talk about how's it called? Linear algebra, you have your base field, and then you have your vector space. Okay, and so you have two sorts. You have the elements of the vector space and the element of the base field. And you want to have a theory that actually has this difference between like different kinds of objects. And you can actually kind of even generalize this by saying that not only do you have kind of multi-sorted things, but actually these things can be kind of indexed by others. So here, kind of the one way of setting up what I showed before is saying that we have a sort of context, and we have a sort of types, but this sort of types kind of is indexed, is like we have not just one sort of type, but for each context, we have a sort of type in that context. And then terms would be like for each context and type, we have a set of terms. And then these definitional equality would be becoming the usual kind of equation that you have in this universal algebra. So I'm not going to go to that level that much, because anyway, I want to kind of stay there, because first it's a bit less abstract, so maybe a bit easier to understand. And also because this is the level at which our type checker will work anyway. And so since this is the things I want to talk about, this is kind of a nice level to work. But this is a kind of a nice, powerful mathematical setup for this as well. Okay, and so now I can get into the sort of properties that we care about for these systems, okay? Because it's nice to have all of this kind of theoretical setup, but it's even better if we can actually do things with them. So this is kind of the sort of properties that we typically care about. Okay, so the first is logical consistency, which says that we can't prove all things, okay? I mean, there are many ways, different ways to talk about it, but this is maybe the one that requires the least setup, okay? There are things that we cannot prove, which is quite nice, right? Because that means that we're not doing something completely devoid of meaning. And the other thing that usually we care about is that we can check that a proof is valid or that the term is well typed, okay? Because otherwise we wouldn't be able to actually build the tool that we use, like all the proof assistant we use. So we really want this whole setup to be maybe kind of very powerful and expressive, but also not too powerful, because we really want to be able to still kind of delegate the work to the machine, and the machine is not that smart. Or at least it's smart in different ways. And then there are other things that are maybe a bit more blurry, but that I think are also worth mentioning here. One thing is that we want to have some sort of model. So ideally, one that this sort of logic that we're working with has some sort of interpretation. And then some people care about just the one model, and they're happy if there is just the one model. But actually, this setup is a nice one to do what's called sometimes synthetic mathematics, so kind of abstracting away the details of a particular field of study in kind of a nice language that will talk about various models in that world. So for instance, it's a very good way to think to work about with like homotopy theory. So where you want to think that all the functions you can construct are continuous. And if you try to do that, you can get quite far in a setup with like just kind of doing abstract logic, but remembering that all the things you're constructing are continuous. You can do similar things with computability theory, where all the functions you construct are computable. And so here we can have various different models which will correspond to slightly different variations of the logical framework.
Do you have something similar to extensionality or not?
So extensionality would be so typically the way you introduce it, you mean function extensionality? Or
as in like something similar to like inset theory?
So it depends. Typically so how to say this? So typically in the long list of the things that you want to add in your kind of types, there's probably one equality type, which is saying when two things are equal, but from the point of view of the logic, okay, which is something that you can prove, that you can assume, that you can manipulate in this way. And then the exact rules that govern that particular equality type would be also things that you'd add here, typically. So either as typically as these kind of introduction or elimination rules. Okay. And there are all sorts of flavors of different equality that all have various different advantages and disadvantages depending on what sort of models you want to work with and these sort of things. Okay. So, but they would leave it at that stage, the logical equality.
So if there was some sort of extensionality,
it would be here. So you'd probably have maybe an extra introduction rule saying like, oh, I have this extensionality property. Okay. Yeah. Okay. And then the other kind of the counterpart to that is that typically the weaker, the most restricted the logic, the more models you have, okay, because you're asking for less things. But then this kind of the counterpart to it is that there's also this kind of expressivity thing, which is again very blurry, which means that we can kind of express our logical thinking kind of directly in the system, okay? And so typically you don't want to fight the system to kind of force your ideas in some sort of convoluted way to make it fit. And so that's also kind of a balance between this, having a very expressive system which will have less models, or something which is more restricted, which will have more models, maybe the things you care about, but will have less complicated types, for instance, or things like that. So this kind of a tension that type theorists are faced with kind of all of the time. And then I'll go into kind of more technical things a bit later on, so I can already start talking about the maybe more technical properties that one might care about, and I'll tell you a bit more why these properties can be useful. One is this canonicity property, which I've mentioned before, and that's kind of a computer sciencey thing, maybe. The idea is that you want that every closed term is equal to a value. So kind of a concrete example of this is that whenever you have, so closed means that the term doesn't contain free variable, okay? So it's kind of, it can contain all sorts of applications and functions and so on, but there's no free variable left in it. And canonicity for Booleans is that if you have any term of the type bool, then that term is either equal to true or to false, okay? So the two base Booleans. And there's many ways to think about this, but one way to view this, which is maybe the computer science side, is to say that somehow you can evaluate any Boolean and actually get a value which is going to be one of the two basic Booleans, which are true or false, okay? And some people care about this, some don't. It's also very important for constructive concerns. I mean, so this is really kind of a closing, right? So just a fully finished expression that mentioned nothing from the outside. Then we can have maybe more refined version, which is typically more complicated, but also quite useful for decidability purposes, especially, is that every term, so not just the closed ones, but every term, so those that can mention variable, are equal to some of these normal forms. So kind of a generalization of value that can also kind of embed variable in some way. And I'm not going to define this properly because it's quite tricky. But the idea that you should have here is that this is some sort of symbolic evaluation, if you want. If you've used some of these like PariGP or like all these algebra system, they're very happy in kind of normalizing all sorts of algebraic expressions for you, even kind of polynomials that contains all sorts of variables or like things like this. This is basically what normalization is doing, that you have a way of evaluating all of your expression and get one of these nice normal forms. Yes.
So for canonicity, if you have a term that's not closed,
Yeah.
you just abstract over the three vectors.
Yes, but then the thing is that typically the values at function types are things that start with a lambda and then have something below it, but that something is not specified. And so basically something that like you're not asking for a lot, or I mean, you're asking for something, but this is like, the point is that this statement is really about closed things. It's really not something that talks about variable. So like variable might appear in the definition of T here, but the point is that like at the end of the day, we want to get something that's completely variable free. And whenever variable enter the realm, say like, no, I don't know how to do it. And this is why normalization is much more powerful, because it's much more complicated that way, because it has to deal with like variables and functions that like are not like unknown in some sense.
How do you define a value?
Basically, this is actually part of like this story here. So whenever you introduce a new type, typically like introduction, like values are basically things built from introduction forms.
Okay.
More or
so
less.
So you have like some kind of, so you have like something that's saying, okay, we're defining these things are defined whatever.
Yeah. So and I mean, so this is also part of this tutorial. You never introduce a new type, you kind of have to think a bit about what sort of values you want if you want your canonicity theorem to be true. Yeah. Yes.
So what was it? You expressed some relationship between normalization and canonicity. Can
Yeah.
you just restate?
So basically normalization is a generalization of canonicity where you remove the constraint that the terms have to be closed. So here,
Yeah.
this term lives in the empty context. And normalization would be for any Boolean in whatever context, I have something to which the Boolean is definitionally equal, but then that something can be more complicated than just true or false.
I'm just thinking like, because lean seems to not be canonical considering that we have
No.
commuted.
Well, I mean,
like-
a reasonable fragment of it
Yeah.
is most likely, yes.
But when you apply like non-computable functions, then some.
Yeah, exactly. That's the core of the issue, yes.
But isn't lean still normalizing even with the non-computable function?
So the thing is that basically an axiom is basically something that makes you live in a non-empty context.
Okay.
So that's basically the same idea.
Oh,
so-
so the second you introduce an axiom,
You've lost canonicity, but you can still very much have normalization.
Okay.
It's just that like, now the normal forms of your Booleans are going to be much more complicated because they can use the axioms in all sorts of non-computable ways. And now like the shape that they have is going to be more complicated.
Yeah.
But you can still have a nice normalization property even in the context of the axiom. That's the whole point of normalization. But that's also why it's harder to work with, because like you have to do a bit more things. Okay, and so I've already started talking about ideas like some sort of evaluation of some kind and so on. So the last property that I'm going to introduce, and again, you'll see why I care about this later on, is the subject reduction property. So the idea is that if you view these terms as some sort of programs, you can evaluate them, which is what this reduction relation is doing, is basically corresponding to some sort of program evaluation, okay? And what subject reduction is saying is that basically this computation on untyped programs, which is the typical thing that you do in your type checker, for instance, you don't keep track of types all of the time, is actually included into this definitional equality, okay? So somehow this is saying that the whole setup of the logical framework in terms of this directed equality rule, which has all of these fancy things, agrees, or at least contains the program evaluation, okay? And this is, again, like from kind of the more implementation side of things, it's a very useful property because it's basically what lets you get off the ground when you're trying to use this evaluation relation, which you really want to use when you implement. Okay, so that's kind of the sort of properties are generally kind of nice to have. And now let me try and get into a bit of meta theory. So like how we can prove some of these properties or how they relate to each other in some sense. Okay, so the first one, this kind of logical consistency, maybe the one we care about the most. How do you prove that? Although actually, maybe I should mention that usually people that want to view this as a programming language don't care that all types are inhabited. Actually, kind of like types that are not inhabited are not very interesting from a computer science point of view, because like they could always as well not be here. If you can't build programs that live in them, they're not very useful. So, but from the point of view of logic, it's still quite useful. So one way to prove consistency is to build a model, because like if you interpret one of the type of your type theory in something that's empty in the model, then and like all terms of this type would be interpreted by some inhabitants of that thing. And I'm not saying set on purpose here because you can have models that are not set theoretic, but still, like if you have some sort of emptiness, you don't know that there aren't anything in the interpretation of the type, then you can't have any term that inhabits that type. So that gives you the typical proof that something that your logic is consistent. You can also obtain consistency from canonicity, actually, which is kind of the more syntactical proof. And the idea is that if you have a type, typically like a false type or an empty type or whatever you want to call it, and so and you assume this type has some sort of inhabitant. Now by canonicity, you know there will exist a value of that type. Okay, but the point is that you want to choose this type so that it has no value. So typically, an inductive type with no constructor would fit this thing here. And since this type has no value, then this is not possible. Okay, and so you conclude that there cannot be any term of that type whatsoever. There cannot be any proof of false because there are no canonical proof of false. Okay, and this is a very powerful way of doing this. And kind of one that doesn't need to be a particular kind of model. So that's quite nice. Although sometimes you still want to do this for other reasons, as I said before. But it's kind of a nice alternative. Okay, the second question, which is maybe much more complicated, which is actually kind of the reason why I'm doing all what I'm doing, is how to get this decidability property. And the problem is that the way we set up the rules of the system are kind of very generous. So for instance, this conversion rule here is quite nasty because it's saying that like, oh, you can change the type to whatever other type that you like in kind of some sort of arbitrary way. And then here you might do it again and again and like do all sorts of things and goes through all sorts of types. And from the implementation point of view, this is very crazy, right? Because like there's no way you can kind of, what's the flow of information here? Where do you get this new type from? What's happening here? And so kind of the general, I mean, there's various ways of setting this up, but kind of the general keyword here is called bidirectional typing. So it's a way of kind of arranging your rules to kind of constrain this conversion rule, especially to only apply in places where you have enough information to know what you're doing. So typically here you'd be able to use that full-blown comparison between two types only when you know the two types that you're looking at. But sometimes you only know one of the two endpoints, and then you still need to do something. And that's typically where this reduction or evaluation would kick in. Because like if you know only one endpoint, one thing that you can do is evaluate it to something simpler. And hopefully that will help you in some way. And so this is where a kind of subject reduction starts to be useful. Because you want to know that your evaluation, like if you get the type A from T, for instance, and you want to evaluate it somehow, you still want to know that this is the rule that applies behind the scene. And so this is where subject reduction is useful. Even nastier is the transitivity rule. So again, here we have those problems like what's the flow of information? And the problem is that now this A prime can kind of come from anywhere around and like we don't have a way to guess it. And so actually the way the typical conversion checker works, more or less, is doing something like this. To check whether two things are equal like this, rather than kind of applying transitivity, symmetry, some congruences, some of the other rules kind of at whim, you're going to do something much more structured. You're going to first evaluate your two types to some sort of normal form. That's where normalization is useful. And then you're going to compare them to something that contains these kind of extensionality laws, this eta laws from before. Okay. So basically, like this is the part that takes care of beta. And this is the part that takes care of eta, if you want to think of functions. Now, for this strategy to work, there's a bunch of things. So first, again, we need subject reduction to know that this evaluation here actually will give us things that are definitionally equal. The second thing is whether this normal form here always exists. So again, this is kind of a slightly more refined version of normalization, because we're not talking about definitional equality anymore. We're talking about evaluation, which is something a bit different, but still this is kind of lives in the same world. And one way to get this, and I think given time, I'm not going to go into too much details of this, but one way to get this is to show that basically, if you have any type, then either it's already one of these normal forms that we like, or you can kind of go further in computation. You can make another step of computation. So it, like things don't get blocked in some sense. And then you still remains to show that this terminates, and this is kind of where normalization would happen. But already progress is actually quite nice and gives us quite a lot of leeway. And the last thing is that you need to know that, well, this normal form is some sense unique up to eta at least. So that you know that this strategy is in some sense complete. And then, I mean, I won't go into more details here. I mean, there's been like 40 plus years of research on how to do this smartly in some sort of efficient way, maybe not going all of the way to the normal form and doing this in kind of maybe some smarter fashion and so on. And I mean, there's like a whole area of research around this question of how to build this type checker. But kind of the core idea is this one here, okay? And now, okay, I won't get into this because I see that, okay, so maybe see, okay, for subject reduction, I can get a little bit. So I can show you, so, okay, so the thing is this, okay, so we have this is kind of the core thing. So we have this, what's called the beta reduction, so something that we want to apply this beta rule to, which will evaluate this function by replacing the variable by the argument, okay? And now if we know that this typing judgment holds, we can kind of look at it and use as the rule that we can use to derive it. And then hopefully we can kind of get something like this. Like we know that for this to be well typed, well, T has better be well typed, and then it has some sort of extended context and subtype B. And also U has to be kind of well typed and an argument. And then somehow the type of this whole thing, which is this function type, has to be somehow related to the type at which the application lives, which is this function one. And then the whole type of the whole thing is related again to this thing here. Okay. And this is kind of, I mean, this step is looking at like your inference rules, and if you set up things in a reasonable way, you'll be able to get this sort of things out of it. And then if we want to show now this definition of equality here, so first we can kind of change that, you can use this thing to kind of change the T back to the kind of substituted thing, which is kind of more what we were expected as the type of this whole thing. And now we want to use the beta rule here, knowing that T has type in extended context and U has also the type of its argument. The problem here is that actually types don't really agree. If you look at what's happening here, T has some type B, and here it has some type B prime, and same for U, it has not the right type. And then we knew that these function types are equal. But then if we want to actually change the types from the assumption that we have here to the right one, we want to use this conversion rule on each side to kind of change the B to the B prime and the A prime to the A. But the problem is that we don't know that the A's and the B's are equal. The only thing that we know is that the two function types are equal. And so actually the hard property to show subject reduction, the really kind of crux of the proof of subject reduction, is the fact that these function types are injective, okay, for definitional equality. So that if you have these equalities, you can deduce that A is related to E prime, B is related to B prime, then you could stick this in this conversion rule here and show your definitional equality, okay? And like, I'm not sure this is very convincing that this is really the crux of the proof, but tell me I've done this enough that this is really the core problem whenever you try to prove subject reduction. And yes.
So just trying to remember in my head the
Yeah.
terms straight. So the canonicity was all those terms are kind of values.
Yeah.
The normalization was
Open terms have some sort of canonical thing, but there's like these normal forms which are more complicated than values.
This may or may not be underneath the lambda.
Yes. So like
Usually not, but.
yeah. So for canonicity, you don't have any variables around. So nothing under the lambda, you're like unknown land. But normalization, you can do things under lambdas.
Subject reduction is building on top of these concepts by.
So subject reduction is something kind of different, is saying that like your notion of evaluation that you have from your thing as a programming language is type preserving.
Oh, so the
in some
type
sense.
plus the operation semantics is something.
Yeah, is this definition, it agrees with this definitional equality. Yes. Yeah. And then for progress, we have a similar story. And here, the important thing is this no confusion of type constructors. So the fact that if you have two different types of, for instance, natural numbers and the definitional, and the dependent function type, they are not definition equal. So this situation cannot happen. You cannot have 0 applied to an argument. And again, this is the hard property. And this is maybe not very convincing, but trust me, this is the hard property that we have. So to kind of wrap all of these things up, the essential properties, the ones that are really hard to prove, are these kind of 3 sort of flavors. So these injectivity properties, these no confusion properties, which are kind of related, right? Because the injectivity is some sort of like, all of these things are like, oh, if I know that this type is definition equal to this other type, can I deduce things from this? And here, this is like, oh, this cannot be. And from this one is like, oh, the sub things are related again. And then normalization is also kind of something that I didn't attempt to prove for good reasons, because it's also kind of in this list of hard things. And kind of the message is that this is basically kind of the core difficult things that we want to do a big theory for. So basically, if you're able to show these things, mostly you're probably going to be able to get subject reduction and progress and canonicity, or at least some form of normalization if you have axioms, but like still things will be reasonable. You can probably get some sort of decidability of things out of this, kind of soundness with this kind of syntactic proof. There are more complicated things. There are kind of caveats to this. Terms and condition may apply, but that's kind of what I want to tell you is that these are the hard properties that we want to typically prove. And now I have 5 minutes left. So I just leave you with the question of how do we show that? And I'm just going to throw that word, logical relations. And this is where kind of the fancy math happens, basically. And yeah, so like you define these kind of fancy relations that are some sort of kind of very specific kinds of a model. And there's a lot of complication doing this with dependent type, but at the end of the day, mostly you can kind of do that, although there's a lot of very nasty words on there if you want to do this. And again, there's like a whole cottage industry of how to do these logical relation proofs. But the point is that, like, I mean, this is interesting math, right? There's like fancy category theory that lets you do some of this. This partial equivalence relation is also very useful. Descriptive quantification comes from the world of like constructive mathematics. I mean, there's a lot of fancy things here. But at the end of the day, we can get all of these properties, these kind of essential properties that we wanted as kind of consequences of these logical relation in this fundamental theory, which is one big theory we want to prove. And yes, so that's kind of the array, maybe, I don't know. I mean, I mean, this is like what I do in my life for fun and profits, right? Doing all of these fancy logical relation proofs and then formalizing them in a proof of system, which is even more miserable. But like, I mean, you can get that. There are actually other ways. So the problem of logical relations is that they prove normalization, which lets you prove logical consistency. And if you've ever heard what Gödel has to say about this, is very not happy about a system being able to prove its own consistency. So if you tell him like, formalized talking talk, you're going to look at you with this very distorted eyes. The other problem is that like this is our actual type of terms in MetaCoq, and then I won't show you the typing relation because it's going to take like fill in a few slides. This is kind of a hardcore thing, and I really don't want to do a logical relation for this whole thing. So there are other proof techniques. So in this case, what we're using instead is called confluence, which gives us all of these injectivity and no confusion properties. It scales much better to like much more complicated system. But we don't prove normalization, which in this case is kind of a feature, but it's also a bug if you care about logical consistency, but well, I mean, Gödel. And we don't really know how to treat eta well in this setting. So there's also kind of interesting research ongoing in this world on how to be able to have this stored with eta laws. And now, okay, I have 4 minutes left, so I think I can get back to the very beginning and the story about coercions and how kind of they would fit in this setting. So the idea is that what you want as a user is something very transparent like this. Like this is the kind of a generalization of definitional equality, which is now a pre-order. And this is kind of your QE thing that you had in Lean before, right? This is saying that you can coerce from type A to type A prime, and it's a pre-order because sometimes you can't go back. Okay, and as a user, you just want like, oh, the type system can kind of figure out where to put these things in the right places, and it's fine, and it's smart enough to do that. It's a bit too wild, of course, because like now, like the type checker has a lot of responsibility to put these things in place. What's maybe a bit less scary is this coercive subtyping, which is kind of closer to what I actually showed at the very beginning. And the difference is that you still have this subtyping judgment here, and you still have basically the same two premises. But the difference is that now you record the fact that you inserted one of these coercions, okay? And this is kind of the thing that's less frightening. Also semantically, it's much easier to build models of these things because now you have kind of more data around to work with the thing. It's more reasonable for the implementations, less scary, and so on. So this is nice. That's what we want to have somewhere. But users don't want to do that. They don't want to put all of these coercions by hand all over the place. And if you're a type theorist, you said this is work for the machine. I mean, that's the whole point of coercions. Want the machine to insert them in the right places. And so like, okay, fine. Let's just try to elaborate in some sense. So like take something that would be tight in this kind of crazy type system with this kind of, without these coercions, and then generate something, a new thing that would be typed in this thing, but now has all these coercions in the right places. What could go wrong, right? You have a whole typing derivation here, you have all of these judgments here, so you just insert coercions in the right places and you're done. The problem is that actually, that's called coherence, is that you want to get an unambiguous result here, right? Potentially, there are many ways you can type something by putting subtyping in different places. And since you don't record subtyping here, there's no way to distinguish these different derivation trees. While here, you really want to have coercions kind of unambiguously put in place. And it was exactly the problem that we had in Lean at the very beginning, was that there was two different ways of putting these coercions in, and they didn't agree. So in particular, subtyping is transitive. It's a nice reorder. And so the question is like, now we can exactly reproduce the same problem that we had before. You can pass from a type A to a type A prime, and then from A prime to A second, or directly from A to A second. You have this transitivity problem, like what are you going to do? How do you relate these two things? And well, now we have this definitional equality, so we know what we want to do between them. But then can we design a type system here that has all of these transitivity equation and still kind of has all of the good properties? And another way to say this is that we have kind of one way, easy way to go there, which is just remove the coercions. And then we want to have some sort of section or retraction. I never know which one is which. In the other direction, that's the compilation we want. And it's only well-defined and type preserving if a lot of equations hold, because the problem of dependent type theory is that if you don't have enough equations, then type checking is going to get mad and things are not going to work well. So in particular, if two things have the same erasure through there, then they better be a definition equal. This is yet another way of rephrasing the coherence property here. And actually, that's where I pretend that I'm a mathematician, I write theorems. We have like the kind of the last paper I wrote, where we can kind of design this kind of nice type theory, which with all these coercions that has all of the good properties. I mean, maybe not the models bit, but at least all of the essential properties like normalization, injectivity of our constructors, all of that. And that is flexible enough, has enough of these equalities to admit this kind of type preserving elaboration from the type theory that users want to have. So this is the sort of theorems I show in my life. And the key thing, and I'm going to maybe leave you on some sort of mysterious thing, is basically this functoriality thing. So to teach the kernel about this functoriality equations, but in the definitional equality. And if you're able to do that, and you can do that while keeping all of the good properties, then you can design a coercion system in a way that has this nice property, that has the coherence thing, and everything works well. I mean, there's still caveats because this language is also kind of not as fancy as like the actual thing that we implement. So Arthur here is going to work with me for a bit about trying to make this whole story nicer. But hopefully one day we'll have a better theorem and maybe we'll make our proof assistance better using all of these fancy things. And that's it for me. Thank you.
Yeah, thank you so much for this talk. We have questions.
Yes.
So why do you, as a design rationale, why do you want to separate the universal proposition from the general universal types?
Because it obeys different rules. So for instance, in mean, propositions are definitionally irrelevant. So any two propositions are definitionally equal. And that's a very powerful property and very useful in quite a lot of settings. but you don't want that for your relevant content. Like you don't want any two booleans to be equal. That would be kind of defeating the point. And so the idea is that if you have propositions in a different universe, you can have this definitional equality business just for that particular universe, but not for the others. So it's typically the sort of, I mean, the two reasons you want to have these universes. One is this kind of business where you want to avoid this like kind of self-referential paradox, like Russell paradox or whatever. That's one big theme. And the second thing is that if you have different universes, they can have different special properties about them. That might not all types might satisfy these nice properties, but some might. And so you're going to use a universe to segregate the nice types that have the nice properties from the others. That's a typical thing you want to do there. Yes?
This is more of an organizational question, but
Yeah.
you post your slides.
We'll put
somewhere.
them, so I will put them on my website for sure.
Yeah.
I can do that. And then I don't know if you have a, okay, I'll send them to the organizers and they can do the link. Yes,
With regards to logical relations,
yes.
how extensible are they in the particular sense that the one formalized in Martin-Löf MetaCoq is MLTT with one universe and a Russell, whatever. How complex is it, for example, to add impredicability or arbitrary types?
So there's basically two things that can happen. If you're on the lucky side of things, the kind of general way you define your logical relation is kind of powerful enough that you can just add your new type and add kind of new cases for it in the logical relation, and everything else can stay unchanged. And if you do that, basically you're happy because you only have to add kind of a few cases in the right places and everything else will work through. So that's the happy path. And it's still painful, but at least you kind of contain the painfulness to the new thing that you've added. So that's what we did, for instance, in this subtyping thing. We've extended the logical relation we already had from before to just a few new cases. The sad path is when you have to redo the entire logical. So typically when you changes are going to touch to like the logical framework basis, like the way you set up the like judgmental structure or things like that, or the sort of properties that you want to get out of your logical relation are going to change. Then you're going to have to change the definition of the whole logical relation. And then typically you'll have to reprove a lot of new things for the old type formats that you had. And that's kind of the sad path, and that's where you need to suffer a lot more. And in practice and formalization, they tend to be less kind of modular than in pen and paper. You can just say like, oh, we extend the logical relation of that paper with these new cases, and like engineering wise, it's also a bit more complicated. But yes, I mean, they're like, yeah.
Mainly wondering, because I know that Loic, for his observational equality one,
Yeah.
did manage to add
Yeah.
predicativity, but
Yeah.
the computational power of the theory stays the same.
Yes.
If you were to construct a logical relation for something like the calculus of construction,
Yeah.
with an accessibility predicate, so
Yes.
something in which
Yeah.
adding in predicativity would make
Yeah.
your theory much stronger
Yeah.
in the theoretical sense, would logical relations still hold up to that challenge?
So you'd probably need to change your logical relation quite a bit, and probably also make sure that your meta theory is strong enough to define a logical relation that's powerful enough to show the normalization that you want. Which is also kind of the problem of the logical relation, is that typically in this sort of setting, you're always flirting with Godel. So you always need to know that like the ambient theory in which you're setting up your thing is going to be powerful enough to prove at least the logical consistency of your object. And typically that means that if you achieve a logical relation that is able to show normalization, you will have to use some of these very powerful principles. And so typically there's a point where you need to kind of tie the knot around like universes or something like that. And you know some of this problems, you really kind of the one pain points where you really have to be very like typically invoke some of these very powerful logical principles of your ambient theory to be able to make your logical definition. But I mean, again, there's a whole like cottage industry of this and like all sorts of various setup and kind of some people have tried to have kind of generic setup for logical relation are kind of, I mean, there's a lot of things there. Yeah, with various advantages and disadvantages.
It's already 5 past, so
Yeah.
everyone has to leave right now, so if you want to stay. But maybe there are also questions online.
Yes, I can check. What's happening? I know, okay, this is my mouse. Are there online questions? Isn't no confusion theorem that one can prove from the eliminator? Ah, good question. So the eliminator has nothing to say about definitional equality. What you can prove with the eliminators are things that you can prove about the propositional equality, so like the one that you can logically manipulate. And they're two very different things. And so the eliminator has nothing to say about the definitional equality. That's the first thing. And the second thing is that typically universes don't come with an eliminator for kind of good reasons. In some sense, we want to keep them open because it means, for instance, you can define new types as you go. And so you don't want to have an eliminator is in some sense saying that something is closed, that you have like, all of the values that things can take in there. So typically universes don't come with eliminators. And so you can't prove these, you wouldn't be able to prove these no confusion things internally in a typical setup. But in any case, these no confusions are really things about the definitional equality, which is a separate business. If that answers the question.